Imagine robots stepping off the assembly line floor, out of their cages,
Yeah.
and into the messy, unpredictable world right alongside us.
Yeah, it's a pretty big shift.
Imagine talking to a robot, not using some clunky interface,
Mm.
but just speaking.
Hmm.
Asking him to grab you a coffee or tidy up a workspace, maybe help with a complex task.
And it actually understands, even if you're a bit vague.
Exactly. It gets the intent.
That future, the one that feels, well, straight out of science fiction, it's arriving faster than most people probably realize. It signifies a really profound transformation in what robots are capable of and, where we'll actually encounter them.
And this revolution, this shift toward robots that aren't just programmed tools, but increasingly capable sort of cognitive partners, it's being driven by the powerful convergence of large language models, LLMs, and the world of physical robotics.
Absolutely. And it's way more than just like sticking a chatbot interface onto a robot.
Right. It's deeper.
It's about integrating that sophisticated AI understanding directly into the robot's operational brain.
Okay, so for this deep dive, we've been digging through a whole stack of source material. We've got market analyses, foundational robotics concepts, deep looks at the companies actually building these things.
Yeah, and projections on where it's all heading. It's a lot to synthesize.
It really is.
Yeah.
So our mission today is to guide you through that material. We want to distill the most crucial insights, help you really grasp the core of this LLM-powered robotics revolution.
Understand who the key players are right now.
Yeah, and explore the potential trajectory of this field because it's moving incredibly fast. We'll be your navigators through all this fascinating info.
It's definitely a landscape ripe with, well, incredible potential, but also some significant technical and societal challenges.
For sure.
It's complex, it's fast-paced, and it definitely demands our attention. So let's get right into it.
Let's do it. Let's define what this fusion of LLMs and robotics really means. Okay, so let's unpack this. We're calling it LLM-powered robotics, sometimes cognitive robotics.
Yeah.
What exactly defines this new era? Like you said, it's fundamentally different from just adding a chat window.
That's a really critical distinction. At its heart, LLM-powered robotics uses the sophisticated capabilities of large language models.
Right.
Not just for talking, but to enhance the intelligence, the adaptability, and crucially, the problem-solving abilities of the robots themselves.
So the LLM is like a higher level brain.
You can think of it that way, yeah.
Yeah.
A high-level cognitive engine. It allows the robot to move beyond just executing pre-programmed scripts and towards actually understanding goals, reasoning about its environment, and, generating novel actions to achieve those goals.
And just to ground this for everyone, LLMs, we're talking about those advanced AI models, often based on architectures like the Transformer Network.
Right. Trained on absolutely massive data sets of text, and now, increasingly, other things like images and code.
Models like OpenAI's GPT series, Google's Gemini, Meta's Llama, the ones everyone hears about.
Exactly. They excel at understanding context, generating coherent text, finding patterns in language, basically understanding and manipulating human language.
Okay, and how did those specific abilities translate to making robots smarter?
Well, several core capabilities are just transformative for robotics. The most obvious one is natural language understanding, or NLU.
Right.
This is the ability to interpret human commands even when they're complex or maybe colloquial, nuanced, ambiguous even.
So instead of needing like precise code input,
Exactly.
you just say, could you please clean up that mess on the table? Or find the specific tool I was just using.
Right. And the robot needs to understand the meaning behind those words, the intent, not just match keywords.
That seems huge for usability.
It dramatically lowers the barrier to entry for interacting with robots. Then, complementing NLU, you have natural language generation, NLG.
So the robot talks back.
In a sense, yeah. It allows the robot to communicate back to you in a human-like way. It can provide feedback, ask for clarification.
Like which table were you referring to?
Exactly. Or confirm it understood, maybe even explain what it's doing or why.
That makes the whole interaction feel much more natural, more like a collaboration.
It really does. And beyond just the language part, LLMs bring powerful reasoning and problem-solving capabilities.
Okay, how does that work?
This is vital for handling those open-ended or high-level requests that require more than just a single direct action.
Like get the meeting room ready.
Perfect example.
Yeah.
That involves understanding the concept of a meeting room ready, right? And then breaking that down into subtasks.
Arranging chairs, cleaning the table, setting up the video conferencing.
Right. And coordinating those actions logically. LLMs can assist significantly with that kind of task planning and decomposition. They help the robot figure out the step-by-step process needed to achieve that high-level goal.
So they map out the strategy.
In a way, yes. And then that plan needs to be translated into actions the robot can physically perform. This is where code generation or function mapping comes in. The LLM can translate the abstract plan, or the natural language command, into calls to specific functions or APIs.
Stuff the robot's underlying system understands.
Exactly. Or even generate executable code snippets, like Python, that directly control the robot's motors, sensors, or its end effector, its hand or tool.
So the LLM acts as the strategic planner and the translator, converting what the human wants into concrete robotic instructions.
That's a really good way to put it. The typical architecture you see has the LLM as the central cognitive engine or brain. It gets the user commands, processes them using its NLU, reasoning, planning skills, and then it interfaces with the robot's lower-level control system, often through something called function calling.
Function calling.
Yeah, basically telling the robot system, execute skill number 3, or run the grasp object routine with these parameters.
Yeah. But here's where it gets really interesting for me. LLMs traditionally work with text, right? But robots live in the physical world. They have to deal with sight, sound, physics. How do you bridge that gap?
That is the crucial question. And the answer lies in the evolution towards multimodal LLMs.
Models that handle more than just text.
Exactly. Models like GPT-4V or Google's Gemini that can process text alongside images, video streams, maybe other sensor data. These are absolute game changers for robotics.
How so?
By integrating visual and other sensory information, the LLM can ground its understanding in the physical environment. It connects the words to the world.
So if I say pick up the blue box on the left.
A text-only LLM understands blue box conceptually.
Right.
But a multimodal LLM can see the scene through the robot's camera, locate the specific blue box you mean, understand its spatial relationship on the left, and maybe see obstacles nearby.
That makes a huge difference.
It's fundamental. This integration of perception data directly informs the LLM's reasoning and planning for embodied tasks happening in the physical world. It addresses that core limitation of text-only models lacking connection to physical reality.
And that's vital for making good decisions and generating the right actions in, like a messy room or a busy warehouse.
Absolutely. For robust decision-making in dynamic, unstructured environments, you need that grounding.
This feels like it unlocks entirely new levels of capability. So what are the biggest sort of synergies and enhancements that LLMs really bring to robotics?
Well, first and foremost, the vastly enhanced human-robot interaction, the HRI we talked about.
Making them easier to talk to.
Exactly. Natural language interaction makes robots accessible to non-programmers. It opens them up for use in homes, hospitals, retail spaces, factory floors, right alongside people. It just lowers that barrier to entry dramatically.
So anyone could potentially use a robot, not just engineers or technicians.
That's the goal. Another key benefit is improved adaptability and generalization.
Meaning they can handle new situations better.
Precisely. Robots powered by LLMs can handle dynamic, unstructured environments much better than traditional robots that rely on rigid, pre-programmed routines. They can generalize skills to new tasks or situations with less explicit reprogramming. They leverage the common sense knowledge and broad understanding embedded in the LLM's training data.
That tackles a huge historical bottleneck in robotics, right?
Yeah.
Robots being stuck into very specific controlled environments.
It really does. They can start to figure things out on the fly in unfamiliar situations.
Yeah, okay.
Which leads directly to the next point. Advanced reasoning and common sense problem solving.
So they can think things through more.
Yeah. LLMs give robots the ability to tackle abstract, multi-step goals. They can resolve ambiguities in commands or figure out confusing environmental cues. They make more intelligent decisions in novel situations by drawing on that vast background knowledge they were trained on.
And this applies to single robots, but what about, say, a whole fleet of them working together?
That's another area. LLMs can significantly improve efficiency in multi-robot systems, or MRS. They provide a natural language interface, potentially, for robots to communicate with each other at a higher level.
Ah, interesting.
So they could share tasks, coordinate movements, collaboratively solve problems in a much more flexible way than purely code-based communication allows.
It really sounds like LLMs are pushing robots towards a kind of true intelligence, not just executing commands, but actively understanding and interacting with the physical world.
That's exactly the connection to embodied AI. LLMs are accelerating the journey towards embodied intelligence.
Which is AI physically situated in an agent, like a robot.
Right, an agent that perceives, reasons, and acts within its environment. The LLM provides that crucial layer of semantic understanding, context, high-level reasoning.
It turns the robot from, like, a complex machine into something more like a cognitive agent.
Exactly, an agent that understands why it's doing something, not just how to do it based on code.
This is all incredibly exciting, but you hinted at challenges earlier. What are the main caveats or difficulties we need to keep in mind with this approach?
Yeah, there are definitely significant hurdles. A major one highlighted in our sources is the black box nature of some LLMs.
Meaning, we don't always know how they reach a decision.
Precisely. Their internal decision-making process can be opaque, really hard to interpret. For safety-critical applications, think medical robots or robots working closely with people where you absolutely need to understand why a robot took a particular action.
You need predictability.
Verifiability.
Exactly. That lack of transparency is a major concern. You need to be certain the robot won't do something unexpected or unsafe. It's hard to build trust if you can't understand the reasoning.
Makes sense.
Another related issue is that the plans generated by LLMs can sometimes be a bit, well, homogeneous is a term used, or they lack the specific detail and robustness needed for complex, real-world physical tasks.
Like they miss the edge cases.
Or the error handling, yeah.
Yeah.
An LLM might give you a good high-level strategy, but executing that flawlessly in a dynamic physical environment with all its uncertainties, that requires incredibly precise low-level control and detailed planning that LLMs aren't inherently designed for.
So they might know what to do in general, but not the exact physically grounded how in a way that guarantees safety and success every single time. Right. Which often means you need hybrid control architectures combining the LLM's high-level reasoning with reliable traditional robotics control methods for the execution.
A blend of old and new.
Pretty much. Also, the grounding problem we touched on remains a fundamental challenge. What's fascinating here is just how difficult it is to truly bridge that gap between the abstract, statistical patterns an LLM learns from, say, internet text and images, and the concrete, real-world physics, spatial relationships, object properties, and affordances a robot actually experiences through its sensors.
Like understanding that open the drawer involves specific forces, friction, avoiding pinching fingers, based on the actual drawer it's interacting with.
Exactly. That deep physical understanding doesn't just magically appear from training on Wikipedia and Reddit. Robustly connecting language to physical reality is still a very active research area.
And getting the data to train these robots must be tough, too.
That's another big one. Data scarcity and cost. This raises an important question. LLMs need massive data sets, right?
Billions, trillions of data points.
Right. But training a robot, especially for complex manipulation or navigating diverse environments, that requires collecting high-quality, specific physical interaction data. And that's far more expensive, slower, and harder to scale than just scraping text or images from the web.
Yeah, you can't just download billions of examples of a robot successfully making coffee in different kitchens.
Exactly. Getting enough varied, high-quality data for robots to learn truly generalized physical skills is a major bottleneck right now.
And even if you have the model, interacting with it isn't always simple, is it?
No, that's the prompt engineering complexity issue. While the dream is a simple natural language, getting consistently reliable and nuanced outputs from today's advanced LLMs often requires expert-level prompt crafting.
So you need to know exactly how to ask the question.
Right. And if you need to be a prompt engineering wizard to tell the robot what to do, you haven't fully achieved that goal of democratizing robot programming for everyone.
And the LLM's brilliant ideas are useless if the robot physically can't do them.
That's the constrained executional freedom problem. The LLM's intelligence is ultimately limited by the robot's physical form, its actuators, its sensors, its pre-programmed low-level skills. The most creative plan from the LLM is worthless if the robot physically can't execute it safely and effectively. And then you have practical issues. Many powerful models are closed source, API latency can be a problem for real-time control loops if you're relying on the cloud, and the sheer computational cost of running these huge models can be a challenge for onboard embedded systems on the robot itself.
And that sim-to-real gap you mentioned.
Yeah, it persists. Policies trained purely in simulation, even very good simulations, often need significant fine-tuning and adaptation to work reliably in the real world because of subtle differences in physics, sensor noise, lighting. The real world is messy.
So, okay,
Mhm.
LLMs offer incredible potential for that higher-level intelligence, reasoning interaction. But they absolutely rely on overcoming these technical hurdles and integrating tightly with robust underlying physical systems.
Absolutely. The LLM provides the smarts, the cognitive layer, but the robot needs a capable body and brain, the traditional robotics components, to actually perceive the world and execute tasks within it.
Right. So before we look at the specific companies building these integrated systems, maybe we should quickly touch on those fundamental building blocks the LLM is actually connecting to.
Good idea. Because LLMs enhance the control system's interpretation and how sensor data is used, but they don't replace the need for a physically competent robot.
Let's talk about the robot's anatomy, the core engineering that lets it move and sense.
Okay, think about the basic components. You have the control system. That's the central brain processing sensor data and dictating actions.
Could be simple or complex.
Right, from a basic PLC in a factory to sophisticated ML-based systems. This is typically where the LLM interfaces. It provides the high-level commands or insights.
And the control system translates those into lower-level instructions for the hardware.
Precisely. Those instructions go to the motors and actuators. These are the muscles of the robot.
Motors for rotation, actuators for movement generally.
Yeah. Motors often provide rotational force for joints. Actuators is the broader term for anything causing physical movement. Electric motors, hydraulic cylinders, pneumatic muscles, etc. They do the physical work based on signals from the control system.
And to know what's happening, they need sensors.
Critically important. Sensors are the robot's interface to the world. You've got infrared and ultrasonic for proximity sensing, maybe finding nearby objects.
LiDAR?
LiDAR for detailed 3D mapping of the environment, creating point clouds. Cameras, obviously, for visual perception. Tactile sensors for touch.
Feeling things.
Right? And proprioceptive sensors, which tell the robot about its own state, like the angle of its joints or the forces being exerted.
And LLMs, especially multimodal ones, are key in making sense of all that incoming data.
Absolutely. They help interpret the complex streams of data from all these sensors, turning raw numbers or pixels into meaningful information. That's a chair, the surface is slippery, my gripper is closing.
So the robot senses something, the sensor captures it, and the LLM helps understand what it's sensing in the context of the current task.
Exactly. Then you have the end effectors.
The hands or tools.
Right at the end of the robot arm. Could be grippers for picking things up, welding torches, paint sprayers. Their design determines what physical interactions the robot can actually perform.
And obviously, power supply and a communication system are essential infrastructure. Got to have energy and data flow.
Can't do much without them. And finally, the program or software, the underlying instructions and algorithms defining the robot's basic capabilities and behaviors.
And LLMs might even help write or modify some of that software.
Potentially, yeah. Assisting with code generation or understanding existing programs is an emerging application, though reliability is still a key focus there.
Okay, so that's the hardware. But beyond that, there's the fundamental engineering science governing how robots move and interact. Things like kinematics and dynamics.
Yes, absolutely essential for any physical robot. Robot kinematics is basically the geometry of motion, ignoring the forces involved. It describes position, velocity, acceleration.
How things move in space.
Right. Key concepts include degrees of freedom, or DOF, the number of independent parameters needed to define the robot's position and orientation. Think of the number of joints, and how those joints move revolute, rotating, or prismatic, sliding. Forward kinematics is the easier part. Given the angles of all the joints, where is the end effector, the hand?
Calculating the outcome.
Inverse kinematics is the much harder problem. If I want the end effector to be at this specific position and orientation, what angles do all the joints need to be at?
And there might be multiple solutions. Or none.
Exactly. It's complex. Engineers use tools like homogeneous transformation matrices to combine rotation and translation mathematically, and standardized conventions like Denevit-Hartenberg DH parameters to describe the geometry consistently.
Sounds like some serious spatial geometry and linear algebra.
It definitely is. And then robot dynamics brings in the physics, mass, inertia, gravity, friction, external forces acting on the robot.
How forces cause motion.
Right. It relates the forces and torques applied at the joints to the resulting motion, specifically the accelerations. The equations of motion capture this relationship, considering things like the robot's mass distribution, inertia, and velocity-dependent forces like Coriolis and centrifugal effects.
Why is that important?
Well, inverse dynamics is crucial for control. It answers. To achieve this desired acceleration or trajectory, What forces or torques do I need to apply at each joint?
Calculating the required effort.
Yes. For dynamics does the opposite. Given these applied force torques, what motion will result? That's useful for simulation. And the Jacobian matrix is a key tool that relates joint velocities to the end effector's linear and angular velocity and also relates forces.
Okay, so let me try to connect this back. The LLM might provide the high-level goal, like pick up the red ball. Perception systems identify the ball. Kinematics figures out if the robot can reach it and the necessary joint angles. Dynamics calculates the torques needed for the motors to move the arm smoothly and accurately to grasp it.
That's a great summary. The LLM provides the understanding and reasoning, but it absolutely relies on these robust, precise underlying systems built on perception, kinematics, and dynamics principles, all orchestrated by the robot control system.
Right, the system managing everything.
Yeah, the robot control system, RCS, or robot management system, RMS, is the hardware and software that manages the robot's overall behavior. Centralized management, task planning, allocation, real-time monitoring, environment mapping, maybe remote control, health monitoring.
It's the conductor of the orchestra.
Exactly. It's the layer translating the LLM's high-level intent, perhaps derived from natural language, into actual timed physical commands for the actuators.
Using specific control algorithms.
Yes, a whole range. Classic PID controllers, fuzzy logic, adaptive control, robust control methods. More advanced techniques include computed torque control, which uses the robot's dynamic model for precise force control, or even controllers based on neural networks. One source mentioned FIRST robotics competition, FRC teams often use PID.
And robot perception is how the robot builds its understanding of the world from sensor data.
Correct. Gathering that raw data from cameras, LiDAR, etc., and processing it through algorithms, object detection, depth estimation, localization to extract meaningful information about physical properties, objects, spatial relationships. Absolutely crucial for any autonomous operation.
It's not just seeing data. It's interpreting what the data means in the real world.
Precisely. Turning raw pixels or laser points into, that's a doorway I can go through, or that's the palette I need to pick up. Sensor fusion is often key here, combining data from multiple sensor types to get a more accurate and robust understanding than any single sensor could provide.
And perception directly informs what the robot does next.
Directly. A warehouse robot needs to perceive the palette correctly to align its forks. A self-driving car needs to perceive lane lines and other vehicles. It's an iterative loop. Perceive, plan, act, perceive the results, replan.
Which leads us to robot manipulation physically interacting with the environment. Grasping, pushing, assembling things.
This is incredibly complex and a major focus of robotics research. It requires real-time perception, sophisticated planning that accounts for object properties, weight, friction, shape, dynamics, and unavoidable uncertainty.
What are the core components here?
Understanding contact mechanics, how rigid bodies interact, dealing with friction, ensuring things don't pass through each other in simulation or reality. Grasping is huge, how to securely pick up and hold objects. This involves analyzing grasp stability using tools like the grasp matrix, aiming for form closure, geometrically constrained, or force closure, constrained by friction. Even seemingly simple actions like pushing objects controllably are challenging.
So the robot needs to know not just how to pick something up, but how hard to squeeze, how to adjust if it starts slipping.
Exactly. This requires advanced perception and planning specifically for manipulation. Object detection, grasp planning, figuring out the best place to grip, trajectory optimization to move smoothly while holding something, and sophisticated control methods come into play.
Like
Hybrid position force control, where the robot simultaneously controls its position in some directions and the force it applies in others. Imagine inserting a peg into a hole. Or impedance control, which regulates the relationship between motion and force, essentially controlling the robot's stiffness or compliance.
making it yield appropriately when it contacts something.
Right, compliance can be passive, built into the mechanics, or active, achieved through sensing and control. The sources emphasize practicalities too. Research the task. Use quality components, keep software updated, consult experts, train operators, prioritize safety, and perform regular maintenance. These are critical for successful manipulation.
And as these robots move out of factories and into places like homes or hospitals, that interaction with people becomes key. Artificial social intelligence and HRI.
Absolutely vital. This is all about the robot's ability to interact naturally and effectively with humans in shared spaces. Voice recognition is fundamental, but still has challenges with background noise, accents, pitch variations, though accuracy around 95% is often cited as achievable.
Gesture recognition, too. understanding pointing or waving.
Yes, often using real-time 3D data from cameras. Facial expression analysis helps the robot potentially understand human emotions or state of mind. And while truly generating convincing artificial emotions or personality is very complex and perhaps philosophically debatable,
Right?
robots are being designed to respond in ways that improve human comfort and understanding. Think of social robots like Jibo. Even if it wasn't commercially successful long-term, it explored these ideas.
Yeah.
Using appropriate vocal tones or even simple screen-based expressions.
And this is where LLMs really shine, right? Enhancing that social interaction.
Massively. LLMs enable much richer, more contextual, more human-like conversation. They help the robot understand nuances, remember past interactions, and respond more appropriately in social situations. They are a huge accelerant for artificial social intelligence.
Okay, so wrapping this section up. LLMs provide that powerful cognitive layer understanding language, reasoning, planning, which integrates with the robot's fundamental physical systems for perception, control, kinematics, dynamics, and manipulation. It's about combining high-level smarts with low-level physical competence.
That's the core concept. And importantly, this isn't just theoretical research anymore. Companies are actively building, testing, and in some cases, deploying these kinds of systems right now.
And the sources suggest North America is a real hotspot for this activity, leading the global market.
Yeah, the numbers point that way. North America holding around, 34.6% of the global market share in 2024? Estimated at $0.9 billion total, with the U.S. alone making up about $0.77 billion of that. It really highlights the significant investment and innovation happening here.
So let's dive into the trailblazers then. The companies really pushing the boundaries in this LLM robotics revolution. We know there are different types AI enablers like NVIDIA, established industrial players like ABB or FANUC adapting.
Right, they're integrating AI for things like vision systems or programming assistants.
But let's focus on the ones highlighted in the sources that are really emphasizing humanoids or explicit deep integration of LLMs and advanced AI into their core robot design.
Okay, a name everyone probably recognizes is Boston Dynamics.
Absolutely. Famous for those viral videos, Spot the Dog, Atlas the humanoid doing parkour. Incredibly dynamic robots.
Exactly. Boston Dynamics, which is now owned by Hyundai, has a strong focus on dynamic mobility and mobile manipulation, particularly for tasks in unstructured environments, often summarized as the dull, dirty, dangerous jobs outside of clean factory floors.
Their main robots being Spot, Atlas, and Stretch.
Correct. Spot is their quadruped, the dog-like one. It's incredibly agile, built for inspection, data capture, remote operation in tough places like construction sites, mines, energy facilities. It's got 360-degree perception, what they call athletic intelligence.
And it can carry things, even an arm.
Yes, it can be equipped with an arm for manipulation. And importantly, the sources highlight specific LLM integration examples. MIT researchers developed a system called Clio, using LLMs with Spot, allowing voice commands for mapping areas and identifying objects.
So you could tell Spot, go map the kitchen and tell me where the fire extinguisher is.
Something like that, yeah. And Boston Dynamics itself demoed Spot acting as a chatty tour guide, using ChatGPT for understanding the conversation and 11 Labs for generating natural-sounding speech output.
So Spot is definitely getting the ability to understand and respond using natural language. What about Atlas?
Atlas is their dynamic humanoid platform. The newest version is all-electric, a significant redesign. It's built on decades of research into bipedal locomotion and dynamic balance. It uses advanced AI techniques like reinforcement learning, RL, for whole body control, enabling those agile movements, and also for dynamic manipulation.
And they're working on specific AI models for it.
Yes. They have a partnership with the Robotics and AI Institute, RAI, and Toyota Research Institute, TRI, specifically focused on developing large behavior models, or LBMs, for Atlas.
LBM, so not quite LLMs. What's the distinction?
Based on the descriptions, LBMs seem conceptually similar to LLM's large foundation models, but instead of being trained primarily on text and images, they're trained on vast data sets of robot behavioral data.
Movement data, simulation data.
Likely both. Motion capture, simulation runs, physical interactions. The goal is to capture and generalize a wide repertoire of dynamic movement and manipulation skills. So Atlas can learn complex behaviors and combine them flexibly to perform tasks, with a strong emphasis on transferring skills learned in high-fidelity simulation to the real robot that's sim-to-real transfer.
And they've shown Atlas doing factory tasks with these LBMs.
Recent demonstrations point that way, yeah, showing it navigating and interacting in factory-like settings. They also have Stretch, which is more specialized for warehouse case handling and truck unloading.
Their business model seems focused on selling or leasing spot and stretch, plus software like their Orbit platform and services, targeting industries like construction, logistics, public safety.
Right. Spot is commercially available now. The new Electric Atlas is explicitly on a path towards commercialization, moving beyond just research.
And the Hyundai acquisition was for $1.1 billion. One source mentioned annual revenue over $130 million, so they're generating real income.
Definitely a major player.
Okay, next up, Figure AI, a newer company founded in 2022, but they've made a huge splash very quickly.
Yeah, founded by Brett Adcock. Figure AI is intensely focused on creating general-purpose humanoid robots. Their main models are Figure O1 and the more recent, industrially focused Figure O2.
General purpose is the key phrase there, designed to do many different things.
That's the explicit mission. Address labor shortages initially in manufacturing, logistics, maybe retail warehousing, but with a long-term vision for them being useful in retail environments and eventually even in the home.
What are the robots like?
They're electric bipedal humanoids, designed to operate in spaces built for humans. Specs are around 5'6" tall, 60 kilograms, 20 kilogram payload capacity, roughly 5-hour runtime per charge. Crucially, Figure takes what they call an AI-first approach.
Meaning the AI drives everything?
Pretty much. Their system called Helix has historically relied heavily on a vision language model, or VLM. This model takes real-time input from the robot's cameras at about 10 hertz and transcribed speech.
Sees and hears.
And directly outputs commands for the robot's 24 degrees of freedom, basically. The joint movements at a very high frequency, like 200 hertz.
Whoa, so the AI is directly controlling the limbs based on vision and language.
That's the architecture they've described. They aim for speech-to-speech reasoning and true end-to-end action learning. The robot converses, the speech goes to the AI model, historically noted as OpenAI's models,
Right.
which outputs text that informs the robot's VLM, which then decides which learned physical behavior policy to execute. Their really ambitious goal is a single foundational AI model capable of controlling their general-purpose robot across many different tasks.
How do they handle walking and stuff?
They use reinforcement learning extensively for locomotion. They train thousands of virtual humanoids in high-fidelity simulations, using techniques like domain randomization to make the learning robust, and then aim for zero-shot transfer of that walking skill to the physical robot, leveraging fast torque feedback from the motors.
Their whole strategy sounds incredibly data-driven.
It really is. They explicitly state that solving embodied AI is both a data problem and a robot problem. Their plan involves deploying robots for paid commercial tasks.
Generating real-world data.
Exactly. And that data feeds back into improving the AI model, creating this flywheel effect where the entire fleet learns and improves over time from the experiences of individual robots.
And they have commercial deployment starting.
Yes. Their business model targets commercial labor markets first. They recently announced a significant commercial deal to deploy Figure 01 robots at BMW's manufacturing plant in Spartanburg, South Carolina.
Doing what?
Logistics and material handling tasks within the plant. They also mentioned having an unnamed major logistics customer.
And they're building for scale.
Very much so. They've established a factory they call BotQ, apparently targeting production of 12,000 units per year initially, with bold aims to scale that up towards 100,000 within about 4 years.
That requires serious capital.
And they've raised it.
Yeah.
Total funding reported is $754 million. Their latest Series B round in February 2024 was massive, $675 million.
Wow, who invested?
A huge list of strategic players: Microsoft, NVIDIA, Amazon through its Industrial Innovation Fund, the OpenAI Startup Fund, Jeff Bezos personally via Explore Investments, LG Innotek, Samsung's investment group, ARK Invest.
That's a stacked roster. What kind of valuation does that imply?
That round reportedly valued Figure AI at $2.6 billion back in March 2024. Some more speculative reports projected a valuation hitting nearly $40 billion by early 2025, which seems optimistic, but indicates the high expectations.
No, their LLM and AI integration strategy is particularly interesting, especially given that OpenAI investment. What do the sources say?
This is a crucial point. They initially partnered closely with OpenAI, leveraging their models for the VLM capabilities and the voice-to-action pipeline. This raises an important question. How sustainable or optimal is relying on an external, generalized AI provider for such a specialized real-time application?
Right.
Well, according to reports from early 2025, Figure's CEO announced a significant strategic pivot. They stated they would be ending their collaboration with OpenAI by February 2025.
Ending it. Completely. Despite the investment. That's a big move.
It is indeed. The reason given was achieving a major breakthrough in developing their own fully end-to-end robot AI built entirely in-house.
Why the change?
The rationale seems to be that integrating OpenAI's more generalized large models presented significant challenges in achieving the specific real-time, physically grounded control needed for their particular robot hardware and target tasks. They felt a vertically integrated approach was necessary.
So building the AI specifically for their robot, rather than adapting a general model.
Exactly. Preferring to build their core AI intelligence internally to better tailor it to their robot's physical embodiment and the demands of real-world physical interaction. They will still collaborate with partners like Microsoft for cloud computing and NVIDIA for simulation tools, but the core robot brain is moving in-house.
That's a fascinating strategic decision. It highlights a potential tension in the field. Use general external LLMs or build specialized internal foundation models for robotics.
It really does. It suggests that for high-performance, real-time embodied AI, vertical integration might be seen as advantageous by some key players.
Okay, moving on. Agility Robotics is another prominent company in the humanoid space.
Right. An Oregon State University spin-off, founded back in 2015, they're best known for their bipedal robot, Digit.
And their focus is more on logistics and warehouses.
Primarily, yes. Digit is specifically designed to work safely and effectively alongside humans in logistics and warehouse environments, moving boxes, carrying totes, navigating aisles. The latest versions have improved specs, about a 4-hour battery life, autonomous docking for charging, more robust limbs, and enhanced end effectors, like hands with a wider grasp range for handling different types of packages. Safety features are also emphasized.
They also seem heavily invested in simulation and AI, particularly with NVIDIA.
Very much so. They have an expanded collaboration with NVIDIA, heavily utilizing the Isaac Sim and Isaac Lab platforms for high-fidelity simulation, training onboard AI controllers using reinforcement learning for things like stability and step recovery.
Making Digit walk better and recover from disturbances.
Exactly. They use NVIDIA's AI platform for real-time perception and those RL controllers. They're also getting early access to NVIDIA's newer tools, like Cosmos, which generates synthetic worlds for training, and Mega Omniverse Blueprint for simulating entire fleets of robots.
But they also partnered with another AI company.
Yes, and this is interesting. Agility has partnered with Anthropic.
Anthropic, known for the Claude family of LLMs, often emphasizing safety and helpfulness.
Precisely. Agility's partnership with Anthropic is specifically focused on integrating advanced reasoning capabilities into Digit.
Ah, so not just the physical control, but higher-level thinking.
That's what it points to, leveraging LLM-like capabilities from Anthropic to enable more sophisticated decision-making. This would allow Digit to handle more complex instructions, understand context better, and respond more intelligently to unexpected situations it might encounter in a dynamic warehouse environment.
So it sounds like a layered approach. NVIDIA for the physical AI perception, control, walking, and Anthropic for the cognitive AI reasoning, handling novelty.
That seems to be the strategy, yeah. Their business model is centered on commercial deployment in logistics and manufacturing. Ford was an early customer, exploring Digit for tasks like last-mile delivery and warehouse work. They've also had deployments at Amazon fulfillment centers and with Spanx, primarily for tote handling tasks.
And they sell the robots plus a software platform.
Yes, they sell Digit itself and also their Agility Arc cloud platform. Arc is designed for fleet management, integrating and coordinating workflows across multiple robots potentially, including Digit, alongside other autonomous mobile robots, AMRs, from companies like Mir or Zebra, creating a unified system. They strongly emphasize cooperative safety, designing Digit to work within OSHA-compliant environments.
What about their funding situation?
They've also secured significant funding. A $150 million round in 2022 included participation from Amazon's Industrial Innovation Fund, and reports from early 2025 suggested they were in the process of raising a substantial new round, potentially around $400 million, at a pre-investment valuation of $1.75 billion, with firms like WP Global Partners and SoftBank potentially involved.
Okay, let's switch gears slightly to Tesla and Optimus, the Tesla Bot project. This feels like it's coming from a different angle, leveraging their automotive AI work.
Absolutely. Announced by Elon Musk back in August 2021, the vision for Optimus is incredibly ambitious, almost audacious.
Yeah, Musk talks about it being bigger than the car business eventually.
He does. The goal is a general-purpose humanoid robot capable of performing tasks deemed unsafe, repetitive, or just plain boring for humans.
Optimus is their bipedal autonomous humanoid robot.
Correct. The recent Gen 2 version showcase is lighter, slimmer, and has significantly improved capabilities, especially its hands. They now feature independent finger movement and a 2D OF thumb, allowing for more dexterity and manipulation.
What's powering its intelligence?
Tesla's approach is explicitly about leveraging their existing full self-driving FSD technology stack. This includes their custom AI inference hardware, the Dojo supercomputer they built for training neural networks, and their deep expertise in computer vision, motion planning, and controls developed for their vehicles.
They claim Optimus learns just by watching humans.
That's the claim, yes. That it can learn diverse skills by watching human demonstration videos, using a single end-to-end neural network, and then adapt those learned behaviors to real-life physical execution.
What are they showing it doing?
Public demos have included tasks like sorting objects, attempting yoga poses, which got a lot of attention, navigating a factory floor environment, handling delicate battery cells, and even trying some household chores like stirring a pot or vacuuming. Though it's fair to say some early demos faced skepticism regarding the degree of autonomous operation versus teleoperation.
A key focus for Tesla seems to be designing for mass manufacturability and low cost, right? Applying their car manufacturing know-how.
That appears absolutely central to their strategy. Make
Yeah.
it manufacturable at scale, efficiently, like a vehicle. Their business model starts with using Optimus internally within Tesla's own factories as both a proving ground and a workforce augmentation tool.
Training it on the job, essentially.
Right. The long-term vision, though, is massive. Selling Optimus robots to other businesses in sectors like manufacturing, mining, logistics, and eventually selling them directly to consumers for household use.
And Musk has thrown out some truly astronomical numbers.
He has. Projections of $10 trillion per year in revenue eventually from Optimus, leading to a potential $25 trillion valuation for Tesla as a whole. Production targets are equally ambitious, aiming for 1 million robots per year by 2026, with a target price point somewhere in the $20,000 to $30,000 range eventually, although initial costs will surely be much higher, maybe $100 K plus tap.
When might we see them?
The timeline suggests pilot production internally within Tesla starting sometime in 2025, with broader availability potentially beginning in 2026. Musk also mentioned a potential upfront investment of around $20 billion might be needed to scale production effectively.
Now, while Tesla emphasizes their proprietary FSD AI and neural networks, the sheer ambition of a general-purpose robot that learns from observation, performs diverse manipulation, and operates in unstructured home environments. That strongly implies a need for sophisticated AI with capabilities very similar to LLMs, right? Reasoning, language understanding, common sense.
That's a very astute point. Even if they don't explicitly label it as integrating external LLMs like GPT or Gemini, the functionality they are aiming for general-purpose adaptability, learning from diverse inputs, interacting naturally in human environments, necessitates advanced cognitive AI, the kind of capabilities foundation models excel at. So whether built in-house based on FSD principles or potentially integrating other techniques, the underlying AI needs to be incredibly powerful and versatile.
It seems inescapable for that level of general utility. Okay. Next up, let's talk about Sanctuary AI, based in Vancouver, Canada. Their mission also sounds focused on human-like intelligence in general-purpose robots.
Yes, Sanctuary AI, founded in 2018. Their mission is explicitly to create human-like intelligence within general-purpose humanoid robots, aiming to address labor challenges across various industries. Their flagship robot is named Phoenix, currently in its 7th generation.
And they have a key differentiator, according to the sources.
They do. It's their focus on highly dexterous hands equipped with proprietary haptic sensor technology.
So sophisticated robot hands that can feel.
Exactly. Phoenix has hands with 20 degrees of freedom, which is a lot, allowing for complex movements. But the real key is the tactile sensing integrated into the fingertips. They have proprietary sensors, described as 7-cell touch sensors combined with microbarometers, capable of detecting very fine forces down to 5 millinewtons, apparently.
Wow, why is that so important?
It allows the robot to perform complex, touch-driven manipulation tasks with much greater precision and robustness. Think about tasks requiring delicate handling, detecting slippage, identifying textures, or even working accurately without direct line of sight, like reaching into a bin or assembling parts by feel. Their Gen 7 robot has focused on improving uptime, build speed, reducing material costs, increasing range of motion, making the hands more durable, miniaturizing the hydraulics they use, and improving both visual and tactile perception.
So they're really betting that advanced tactile sensing is critical for achieving human-level manipulation and unlocking the potential of physical AI.
That seems to be a core tenet of their philosophy, yes. Complementing the hardware is their AI platform called Carbon.
What does Carbon AI do?
It's their cognitive architecture. It's designed to integrate various modern AI techniques to translate natural language commands from humans into physical actions performed by Phoenix. How it works, according to the description, is by combining explainable reasoning, task and motion planning capabilities, and symbolic logical reasoning.
Traditional AI approaches.
Right, but explicitly coupled with modern LLMs for accessing general world knowledge, so it's a hybrid system.
Okay, so they do use LLM.
Yes, explicitly integrated for that general knowledge base and likely language understanding. Carbon then combines this with domain-specific knowledge, concepts of agency and goal-seeking, deep learning for pattern recognition, and reinforcement learning for skill acquisition. They use sophisticated simulation environments, photorealistic, physics-based, and rely on human-in-the-loop supervision and teleoperation for training and refining behaviors. They also leverage NVIDIA's Isaac Lab specifically for training dexterous manipulation skills, focusing on that sim-to-real transfer.
So Sanctuary AI's approach is clearly hybrid, blending symbolic AI, deep learning, reinforcement learning, and LLMs, all grounded by that advanced tactile sensing in the hands.
That's a good summary. Translating natural language into actionable plans is stated as a core feature of the Carbon platform.
What about their business model? How do customers get access to Phoenix?
Their model is primarily labor as a service. Instead of buying the robot outright, which is very expensive, customers essentially rent Phoenix and pay for the work it performs.
Reducing the upfront cost barrier.
Exactly, turning it from a large capital expenditure, CapEx, into an operating expense, OpEx. They target industries facing labor shortages. Retail is mentioned frequently for tasks like picking and packing, cleaning, applying tags, stocking shelves, but also automotive, distribution centers, and the energy sector.
Are they deployed commercially yet?
They stated their 5th-generation robot was commercially deployed starting January 2023. They also claim their 7th-gen Phoenix can be trained to automate new customer tasks very rapidly, sometimes in less than 24 hours, which is impressive if accurate. They report a growing list of customers and investors.
And their funding.
They've raised around $100 million in total over several rounds. A significant Series A of $59.5 million in 2022 was led by Bell Canada. They also received a $30 million grant from the Canadian Space Agency. They seem to have closed smaller subsequent Series A tranches in 2024. They also emphasized their strong intellectual property portfolio, with one source ranking them 3rd globally for relevant U.S. patents filed.
Okay, one more key player to discuss from the sources. Apptronic, a spinoff from the University of Texas at Austin, also building AI-powered humanoids for industry.
Right, Apptronic, founded in 2016, their main humanoid robot is named Apollo. It's designed as a general-purpose robot, but with a strong emphasis on friendly interaction design, mass manufacturability, a relatively high payload capacity, 55 pounds or about 25 kilograms, and safety features for working around humans.
What are its physical characteristics?
Apollo is about 5'8" tall, weighs 160 pounds, around 72 kilograms. It uses hot-swappable battery packs, providing about 4 hours of operation each. Its design leverages Apptronic's extensive prior robotics experience, including contributions they made to NASA's Valkyrie humanoid robot program.
And it has a modular design.
Yes, that's highlighted as a key feature. Apollo isn't just a bipedal robot. Its torso and arms can potentially be mounted on wheeled bases or fixed pedestals depending on the specific application requirements. It also features swappable end effectors for different tasks.
What about safety and interaction?
They emphasize advanced force control capabilities, allowing Apollo to operate safely near humans by detecting and managing contact forces. It also has perimeter and impact detection systems. For interaction, it uses intuitive visual cues like integrated LEDs and an OLED display on its chest to communicate status or intent. Apptronic provides a software suite designed for a relatively easy point-and-click control and integration into existing workflows.
And their AI strategy. This seems crucial for all these companies.
Absolutely. Apptronic has secured a major strategic partnership with Google DeepMind.
Google DeepMind, another AI research giant. That's significant.
It is. Apptronik's Apollo robot is designated as the exclusive humanoid hardware platform for Google DeepMind's Gemini robotics initiative.
Wow. So Apollo will be powered by Google's Gemini AI models.
That strongly suggests a very deep integration of Google's most advanced AI capabilities, including the powerful multimodal reasoning and language understanding features of models like Gemini, will be central to Apollo's future development for perception, reasoning, and interaction. They are also collaborating with NVIDIA, like many others, using Omniverse for creating digital twins of Apollo for simulation, testing, and refinement.
What's Apptronik's business model?
They are vertically integrated, designing and building their hardware in-house, including critical components like actuators. Their go-to-market strategy is B2B, targeting industrial sectors first. They offer a dual monetization approach. Robotics as a service, raise subscription, which they note is often preferred by logistics customers, and traditional capital expenditure, CapEx sales, which manufacturers sometimes prefer.
What kind of tasks are they targeting initially?
Things common in warehouses and factories: case picking, unloading trucks or containers, downstacking, palletizing and depalletizing, sortation, replenishing production lines, tending machines. They were aiming for commercial availability around the end of 2024 or early 2025.
Do they have customers lined up?
They have announced significant pilot engagements. One is with Mercedes-Benz integrating Apollo into their automotive manufacturing processes. Another is with Jabil, a large manufacturing solutions provider, to use Apollo in their operations. And interestingly, Jabil might also potentially manufacture Apollo robots for Apptronik in the future, leveraging their manufacturing expertise.
And their funding looks strong, too.
Extremely strong. They closed a massive Series A funding round in February 2025, totaling $403 million.
$400 million in a Series A. That's huge.
It really is. It was led by B Capital Group and Capital Factory, but importantly, it included strategic investments from Google, Mercedes-Benz, Japan Post Capital, and also ARK Invest and Ryder Ventures. This round reportedly valued Apptronik at $1.5 billion post-money.
Okay, so reflecting on these companies, it's a really diverse landscape, isn't it? Boston Dynamics, with its legacy of dynamic mobility, now exploring large behavior models. Figure AI, with that super ambitious AI-first, general-purpose vision, and that fascinating recent pivot to fully in-house AI. Agility Robotics, laser-focused on logistics, integrating Anthropic for reasoning alongside NVIDIA for physical control. Tesla, leveraging its massive scale and FSD tech. Sanctuary AI, differentiating with those hyper-dexterous tactile sensing hands and a hybrid LLM AI platform. And Apptronik, with a modular hardware design deeply partnered with Google DeepMind's Gemini robotics initiative.
It's fascinating to see the different strategic bets being made, but the common threads are definitely there: the push towards more general-purpose capabilities, the focus on operating safely and effectively in human-centric environments, and the absolutely critical role of advanced AI, whether explicitly labeled as LLMs or LBMs or VLMs, or integrated foundation models from partners like Google or Anthropic in enabling this next generation of robotics.
These companies aren't just building machines. They seem to be building the very infrastructure for a fundamentally new kind of workforce and human-machine interaction.
It's clearly a highly competitive space, maybe even bordering on a technological arms race. But that competition is undeniably driving incredibly rapid innovation.
Okay, so let's step back now from the individual players and look at the broader landscape. Let's try to synthesize the overall opportunities, challenges, strengths, and weaknesses of this LLM-powered robotics revolution. We've touched on many pieces, but what's the big picture SWOT analysis look like based on the sources?
All right, let's start with the strengths, recapping and maybe elaborating a bit. Enhanced HRI human-robot interaction is huge. Why? Because natural language understanding dramatically lowers the barrier to entry. You don't need specialized training to talk to the robot.
Makes them accessible to way more people in way more settings.
Exactly. Then, improved adaptability and generalization. This means robots can function effectively in dynamic, unstructured environments. Places traditional robots struggle with less need for constant, explicit reprogramming for every little change.
They can handle novelty better.
Yes, which ties into advanced reasoning and problem solving. LLMs bring a level of common sense understanding, the ability to handle ambiguous instructions, and the capacity to plan complex, multi-step tasks.
figuring out how to achieve a goal, not just follow a script.
Right. And there's also a potential strength in accelerated development and prototyping. LLMs can potentially assist developers by generating code snippets, simulating interactions, or helping translate requirements into specifications, maybe speeding up the design cycle.
And overall, the potential for complex task execution is unlocked by this ability to decompose high-level goals into actionable subtasks.
Those are the core strengths the LLM layer really enables.
Okay, now for the flip side, the weaknesses, the significant hurdles that still need to be overcome.
We've discussed several already. The grounding problem and integrating visual perception robustly remain major challenges. What's fascinating here is just how hard it is for an AI trained primarily on abstract digital data, text, images from the web, to truly, deeply understand the concrete physics, spatial relationships, object affordances, and manipulation requirements of the real physical world.
Connecting the symbol chair to the physical object with its weight, stability, the action of sitting.
Precisely. Robustly bridging that gap between abstract language vision patterns and concrete physical reality is still very much an ongoing research effort. Multimodal models are a huge step forward, but perfect grounding is not yet solved.
And the data needed to improve that grounding is hard to get.
That's the data scarcity and cost issue. It's a major weakness. This raises an important question. LLMs thrive on internet-scale data, but how do you acquire enough high-quality, diverse training data for complex physical robot interactions? Think manipulation of thousands of different objects, navigation in countless real-world environments, safe interaction with people in varied scenarios.
It's expensive and slow to collect that kind of physical data.
Exactly. You can't just scrape it. This is a significant bottleneck compared to training models on readily available web data. Then there's the black box nature and lack of transparency we mentioned.
Not knowing why the robot did what it did.
Right. This is a huge weakness, especially for safety-critical applications in industries like healthcare or aerospace, where predictability, verifiability, and explainability are absolutely paramount. You need to trust the system.
And the plans the LLMs generate might not always be reliable enough.
That's the homogeneity or lack of robustness issue. LLM-generated plans can sometimes be too generic, lacking the detailed consideration of edge cases, potential failures, or specific environmental constraints needed for reliable execution in the physical world. Robots often need incredibly precise, context-aware, physically grounded instructions, especially for error recovery.
Getting the LLM to produce those reliable, detailed instructions isn't trivial.
No, which leads to the prompt engineering complexity weakness. While the goal is simple natural language, achieving consistently reliable, nuanced, and safe outputs from current advanced LLMs often requires significant expertise in crafting very specific and detailed prompts. If only experts can talk to the robot effectively, it limits the democratization goal.
Plus, the LLM's intelligence is capped by the robot's physical limits.
Right, the constrained executional freedom. An LLM might devise a brilliant stratagem, but if the robot lacks the necessary sensors, dexterity, strength, or pre-programmed low-level skills to carry it out, the plan is useless. The physical embodiment is a hard constraint.
And there are practical deployment challenges, too.
Definitely. Reliance on potentially closed-source models from specific vendors can be a risk. Dealing with API latency if the LLM runs in the cloud can be problematic for tasks requiring real-time responsiveness. And the substantial computational cost of running these very large models directly on the robot's limited onboard hardware remains a significant engineering challenge. Finally, that sim-to-real gap, while narrowing thanks to better simulators and techniques, still means that behaviors learned perfectly in simulation often require considerable tweaking and fine-tuning to work robustly in the unpredictable real world.
Okay, those are some serious technical and practical hurdles. But balancing that, the opportunities seem immense driving all this investment.
Absolutely. The biggest opportunity is clearly the expansion into new applications and markets. Because LLMs enable robots to handle unstructured environments and interact more naturally, they can move into sectors previously inaccessible to traditional automation homes, hospitals, construction sites, agriculture, retail floors, opening up vast new economic potential.
And that's closely tied to the democratization of robot programming.
Exactly. Natural language interaction makes robots potentially usable by non-experts, by domain specialists who know the task but not coding, fundamentally changing who can deploy and benefit from robotic systems.
We also mentioned enhanced multi-robot collaboration.
Yes, LLMs could enable more sophisticated communication, coordination, and collaborative problem solving between multiple robots working together, perhaps using natural language-like protocols at a high level. Personalized robotics also becomes more feasible robots that can learn and adapt to the specific preferences and needs of individual users.
And the projected growth in key sectors is just massive.
It really is. Manufacturing, especially high mix, flexible production, logistics and warehousing, handling variability, healthcare and elder care, assistance, logistics, service industries. If we connect this to the bigger picture, those humanoid market projections are staggering, going from roughly $304 billion in 2025 to potentially $243 billion, maybe even $372 billion by 2035, 2037.
That's a compound annual growth rate, CAGR, in the mid-40% range.
Yeah, 44, 49% CAGR. That kind of sustained explosive growth indicates a truly fundamental shift, potentially impacting GDP and productivity across many economies.
Those numbers really hammer home the scale of the expected transformation.
They do. And another opportunity lies in the development of foundational models specifically tailored for robotics, those LBMs and VLAs, vision language action models we talked about. Training large models directly on diverse robot interaction data could lead to even more capable and generalizable robot intelligence.
Okay, so huge opportunities, but we also need to consider the threats, the potential risks and downsides.
Absolutely critical to consider these. Safety and reliability are paramount concerns. Unpredictable behavior from a complex AI driving a physical machine capable of exerting force is a major risk. Rigorous testing, validation, and robust safety protocols are non-negotiable.
Ethical implications and societal impact loom large too.
Hugely. Job displacement is an obvious concern as robots become more capable. Issues of accountability, who is responsible when an autonomous robot makes a mistake, privacy concerns arising from robots equipped with sophisticated sensors operating in personal or public spaces, and of course the potential for misuse of advanced robotic capabilities.
Security is another angle, robots being hacked.
Yes, a connected, intelligent robot becomes a potential cyber attack target. A compromised robot could cause physical damage, steal data, or be used for malicious purposes. That's a significant threat. High development and integration costs, while coming down, are still substantial, potentially limiting adoption by smaller businesses. The pace of regulation is often lagging behind the technology, creating uncertainty regarding standards, liability frameworks, and acceptable use cases. Public perception and trust are also crucial. Negative incidents or widespread fear could significantly slow down adoption, regardless of the technological potential. And finally, the intense global competition and technological arms race, while driving innovation, could also lead to rushed deployments with insufficient safety testing, or exacerbate geopolitical tensions around AI and robotics dominance.
So it's a landscape defined by this tension. Immense potential fueled by powerful AI, but counterbalanced by significant technical hurdles, practical deployment challenges, and broad, complex societal and ethical considerations.
That sums it up well. It's a really complex ecosystem driving this forward. Okay, let's unpack this a bit. Beyond the big robot companies, what are some of the key software platforms and other players contributing to this ecosystem?
Well, the Robot Operating System, ROS, seems absolutely foundational for many developers.
Definitely. ROS, and its more modern successor ROS2, isn't really an operating system in the traditional sense, but rather a flexible framework, a middleware, for building robot software.
Providing standard tools and ways for different parts to communicate.
Exactly. It provides libraries, tools like RViz for 3D visualization, ROSBAG for recording and replaying data, build systems like Catkin or Qualcomm launch files for starting nodes, and conventions that allow different software components for perception, planning, control, hardware drivers to communicate effectively using a publish-subscribe messaging system.
And it's modular.
Highly modular. Developers can combine existing ROS packages or create new ones. ROS2 specifically brought improvements for real-time performance, enhanced security features, and better support for multi-robot systems and commercial deployment needs. It provides that essential software infrastructure upon which many LLM applications in robotics are being built. The LLM might handle the high-level reasoning, but ROS2 often manages the underlying communication, device interfaces, and coordination of lower-level processing.
And simulation platforms seem absolutely critical too, especially given the cost and risk of real-world testing.
Indispensable. You simply cannot test every scenario or train complex skills efficiently and safely solely on physical hardware. Simulators are essential. Gazebo is a very popular one, powerful open-source 3D simulator tightly integrated with ROS. It offers robust physics engines for realistic simulation, though it can be computationally demanding.
And then there's the NVIDIA stack.
Yes, NVIDIA has invested heavily here with Isaac Sim and Isaac Lab. Isaac Sim runs on their Omniverse platform, offering high-fidelity, photorealistic rendering and GPU-accelerated physics, PhysX. It's designed for creating very realistic digital twins. Isaac Lab is built on top of Isaac Sim, specifically optimized for robot learning, especially reinforcement learning. It allows for massively parallel simulation, training thousands of virtual robots simultaneously to accelerate learning.
And we heard companies like Agility and Boston Dynamics and Sanctuary AI are using these NVIDIA tools?
Yes, they are key users, leveraging these platforms to develop control policies and bridge that challenging sim-to-real gap. The workflow might involve training in Isaac Sim Lab, maybe transferring to Gazebo for broader testing, and then deploying on the real robot.
Are there other simulators?
Oh yes, many others. Weebots, CapeliaSim, formerly VREP, specialized simulators in MATLAB Simulink, Simscape Multibody. Even game engines like Unity are used for robotics simulation. And briefly, while different, robotic process automation RPA platforms, which automate digital software tasks using UI interactions and some AI, are also starting to integrate ALs. There's potential future convergence where RPA orchestrates digital workflows that trigger actions by physical LLM-powered robots. Companies like UiPath, Automation, Anywhere, SS&C, Blue Prism operate in this space.
If we connect this to the bigger picture, beyond the companies of the software tools, who are the key experts and research institutions really shaping the theoretical foundations and pushing the boundaries of what's possible?
It's a vibrant global research community. Looking at the sources in the area of LLM integration, HRI, and planning, you see researchers like Maliana, Ashok, and Burns working on enabling robots to handle more natural, multi-session conversations, incorporating context, and even understanding human emotions. Anuruddha Majumdar at Princeton is doing important work on safety considerations for AI-driven robots, using examples like ensuring a robot understands the inherent danger of wielding a knife, even if asked to. Ishika Singh and collaborators developed ProgPrompt, a hybrid approach using LLMs to generate structured code for robot tasks, aiming for more reliability. Andrew Hunt at Google DeepMind, formerly JHU, emphasizes the need for extraordinarily high reliability in physical robot systems, a standard that current LLMs often struggle to meet consistently.
And what about those focused more broadly on embodied AI, maybe bio-inspired approaches or foundation models for robotics?
Sergey Levine at UC Berkeley is a major figure. He often notes that while LLMs significantly improve high-level reasoning for robots, achieving full, robust, end-to-end physical autonomy is still a major ongoing challenge. He stresses the critical need for LLMs or similar models to be deeply aware of the robot's physical embodiment, its specific capabilities and limitations. He's a strong advocate for fine-tuning large, pre-trained models on actual robotic interaction data to create specialized vision-language action VLA models, like Google's RT2, which came out of the large-scale OpenX embodiment collaboration he helped lead, involving many top universities worldwide.
Interesting. Anyone else?
Dario Floriano at EPFL in Switzerland, a leader in bio-inspired robotics and flying robots, emphasizes that true intelligence likely requires learning through direct physical interaction with the environment. He expresses some skepticism about a single monolithic robot GPT solving everything, foreseeing a greater role for specialized AIs tailored to specific robotic tasks and morphologies. Marco Hutter at ETH Zurich focuses on legged robots and uses advanced simulators and hardware designs to accelerate learning complex locomotion and manipulation skills. And Brian Gerke, a co-founder of Open Robotics, now Intrinsic Innovation, part of Google, and a key figure behind ROS, consistently advocates for open standards to foster collaboration. He also highlights what he calls the utility dilemma, figuring out the truly useful and economically viable tasks for advanced robots, and raises critical questions about ensuring safety when AI makes real-time, unsupervised decisions that have physical consequences.
And the universities themselves are crucial hubs. MIT, Stanford, CMU, Berkeley in the US, ETH, Zurich, and EPFL in Switzerland, University of Tokyo. They're driving fundamental research and collaborating on big initiatives like OpenX embodiment.
Absolutely. The interplay between academic research pushing the frontiers, open source platforms like ROS providing common infrastructure, and industry driving product development and scaling is what makes this field so dynamic right now.
Okay, so we've explored the foundational concepts, we've met the companies building this future, and we've analyzed the broader landscape of opportunities, challenges, and the ecosystem supporting it all. Where is this ultimately heading? What does the future trajectory for LLM-powered robotics look like?
Well, the overwhelming direction indicated by the sources is towards vastly more autonomous, intelligent, adaptable, and integrated robots. Those market growth projections we keep coming back to are probably the strongest signal.
That leap from $3 to $4 billion now to potentially $243 billion, even $372 billion for humanoids alone by 2035, 2037.
Right. That's not just incremental growth. It signals a potential disruptive transformation impacting multiple industries and potentially society itself.
That scale implies robots becoming much more commonplace, moving into many more aspects of our daily lives and work.
Absolutely. We can expect to see continued increased autonomy and intelligence. This will be driven by ongoing AI advancements, especially the development and refinement of those specialized large behavior models, LBMs, and vision language action VLA models, trained specifically on rich robotic data. They'll get better at interpreting complex scenes, making real-time decisions, maybe even predicting maintenance needs or learning continuously from experience.
And human-robot collaboration will evolve.
Definitely towards what you might call HRC 2.0, much more seamless, intuitive interaction. Robots and humans working together on shared tasks fluidly, communicating naturally using language, gestures, context awareness.
Cloud robotics and the Internet of Things, IoT, will likely play a bigger role too.
Seems probable. Connecting robots to the cloud allows for sharing data across fleets, enabling collective learning, that single brain concept figure AI mentioned. It facilitates optimization, remote monitoring and management, and accessing powerful cloud-based AI models.
AI-driven digital twins and simulation will also become more critical.
Yes, expect increasingly high accuracy, physics-realistic digital twins of robots and their operating environments. These will be used extensively for virtual testing, training AI models safely, optimizing performance, and even predicting potential failures before they occur in the physical world.
And a major trend is democratization and accessibility, making this technology available to more users.
Crucial trend. We see this driven by several factors. Costs are expected to come down significantly. Those bill of materials beyond projections for humanoids are key.
Dropping from maybe $35,000 now towards $13,000, $17,000 by 2030, 2035.
That's the range mentioned. And companies like Tesla targeting eventual consumer price points of $20K, $30K for Optimus, Aptronic aiming for under $50 BOM for Apollo. Even if those take time, the direction is clear. Plus, lower-cost platforms are emerging, like Unitree's G1 humanoid reported at $16,000, or even open-source research platforms like Hugging Face's Hope JR, potentially costing only $3,000 in parts.
And the way people access them is changing, too, with RAOS.
Exactly. Robotics as a service models offered by companies like Sanctuary AI, Actronic, Formic Technologies, Robust.ai, and others fundamentally lower the entry barrier. You subscribe to the robot service instead of buying it, shifting the cost from CapEx to OpEx, making advanced automation accessible to businesses that couldn't afford the large upfront investment. Natural language programming also contributes to democratization.
So with lower costs and easier access, who are the main customer profiles likely to adopt these robots? What domains benefit most?
The potential user base is incredibly broad. Manufacturing, especially for flexible automation in high-mix environments. Logistics and warehousing, dealing with dynamic operations and labor shortages. Healthcare and elder care offer huge potential for patient assistance, transport, logistics within hospitals, maybe even assisting in procedures. Retail for inventory management, stocking, customer service. Education and entertainment for interactive experiences. Defense and public safety for hazardous tasks. Agriculture for precision farming and harvesting. Construction for automating difficult or dangerous jobs. Oil and gas exploration and maintenance. R&D labs.
And eventually, the big one. Domestic and household use, as companies like Figure and Tesla explicitly envision.
That's the long-term horizon for many. Now, which domains benefit most from the specific capabilities LLMs bring, that natural language understanding, adaptability, reasoning?
Good question.
I'd say, first, those operating in highly dynamic and unstructured environments. Homes, public spaces, construction sites, outdoor agriculture places where things are constantly changing and unpredictable. LLMs help robots make sense of and navigate these complexities.
Okay.
Second, domains with a high degree of human interaction. Assistance roles, elder care, healthcare, service industries, retail, hospitality, collaborative manufacturing. Robots that can understand natural language and interact socially are essential here.
Third,
sectors characterized by high task variability or complexity. High-mix manufacturing lines where products change frequently, specialized logistics requiring handling of diverse items, R&D needing flexible automation. LLMs enable robots to adapt more quickly without extensive reprogramming.
Makes sense.
Also, industries facing significant labor shortages or involving hazardous work. LLMs allow robots to take on more complex tasks autonomously, filling gaps and improving safety. And anywhere needing rapid task reconfiguration, the ability to quickly repurpose a robot for a new job using intuitive commands. The specific domains listed frequently benefiting include manufacturing, logistics supply chain, healthcare elder care, retail customer service, education and entertainment, aerospace defense, and R&D.
Okay, so pulling it all together as we wrap up, navigating this dawn of truly intelligent robotics, what are the absolute key takeaways you think people should hold on to, and what's the path forward look like?
I think the core takeaway is that LLMs and related foundation models are genuinely enabling a paradigm shift in robotics. We're moving beyond purely task-specific, rigidly programmed automation towards robots that are more cognitive, adaptable, interactive, and capable of operating in much more complex environments.
But this new intelligence absolutely relies on and must be integrated with strong foundations in traditional robotics.
Critically important. The LLM provides the mind, but it needs a capable body. Robust kinematics, dynamics, perception, control, and manipulation systems are essential for translating intelligence into effective physical action. These aren't being replaced, they're being enhanced and directed by the AI.
And we see a dynamic field of companies leading the charge.
Yes. Players like Boston Dynamics, Figure AI, Agility Robotics, Tesla, Sanctuary AI, and Aptronic are at the forefront, each pursuing distinct strategies, but all heavily investing in advanced AI integration. It's worth watching their different approaches. Figure's pivot to in-house AI, Agility's Anthropic partnership, Aptronic's Google alliance, Sanctuary's tactile focus as indicators of where the field might be heading.
The opportunities are clearly vast, underlined by those massive market growth projections, especially as costs come down and accessibility improves through models like RAS.
Huge potential, and it's a big but significant challenges absolutely remain. The technical hurdles around grounding, data, transparency, safety, and robustness are real and require ongoing innovation. And the broader societal questions regarding ethics, jobs, security, and regulation need careful consideration and proactive engagement.
So, the path forward requires
Continued, intensive R&D is crucial, especially focused on developing those robust vision-language action models, improving sim-to-real transfer, and solving the grounding problem. Standardization, building on frameworks like ROS, will be important for interoperability and accelerating development. An unwavering focus on safety and ethics is non-negotiable, requiring rigorous testing methodologies, clear operational guidelines, and transparent development practices. Hybrid approaches, combining the strengths of LLMs for reasoning with reliable traditional control methods for execution, will likely be key for safe and effective near-term deployment. And finally, society needs proactive workforce adaptation strategies and public dialogue to navigate the changes these technologies will bring.
It's definitely a field marked by incredibly rapid innovation, deep engineering complexity, and profound societal considerations. We're truly watching the beginning of a new technological era unfold.
Yeah, it feels like that. The future of robotics isn't just about building machines that can perform tasks faster or cheaper anymore. It's about creating machines that can genuinely understand human intent, learn continuously from their physical surroundings, and adapt to novel situations in ways that, until very recently, were purely the stuff of science fiction.
This raises an important question then, doesn't it?
Yeah.
As we successfully integrate AI that provides this kind of sophisticated cognitive ability and language understanding into physical, embodied agents, what does that truly mean for the nature of work, for human interaction, maybe even for our understanding of intelligence itself, when it exists not just digitally but physically walking, working, and interacting right alongside us in our world?
Exactly. As LLMs give robots a voice and arguably a mind. How do we define our own evolving roles, our collaborations, and our responsibilities alongside these increasingly capable machines that are actively beginning to shape the physical world around us?